Tests and more tests and more tests. Speaking of tests, Idris, before we talk about any assessment type things, I'm going to pass around the seating chart for this trimester, mostly just so that if I'm gone, a sub knows where to find you and knows how to take attendance, and it just makes it faster for me as well. So if you set it down, you've got the windows, you've got the door. I'm going to tell Harrison where he's sitting, and then everybody else can follow suit from there. Does that make sense?
No, I'm not switching with you.
All right. Today our plan is to talk about homework. Bless you. Goodness. Talk about the homework if you have any questions. We're going to talk about conservation of momentum. We're just going to do, basically today is our day of understanding conservation of momentum. At the end, we'll probably take 5 minutes or so to talk about the survey. The question came up. So this thing says that those questions need to be completed by test day. So when might that be? So let me tell you what I've got on the calendar here. We have, it looks like we are almost done with this unit. So we did some impulse and momentum. We did some impulse and momentum. We did the conservation of momentum lab. I am switching Thursday and Friday because I want a full day to talk about Newton's third law. I feel like one of the Friday days is going to be a little bit more substantial for that. So we're going to do conservation of momentum problem solving today. We'll do the third law on Friday, okay? And then we will be done with this unit, which would line us up to take a test on Monday. I know that you don't all love tests on Monday. Like I can read Ian's face. Can I just be here? That was the face that I saw. I'm fine with moving it back to Tuesday, knowing that we will do new things on Monday. I don't know how y'all feel about that. Is that okay with you? Yes. Would you rather do that? That's kind of what I had anticipated would be the decision, but I want to make sure. So we would test on Tuesday, would be the 4th. December 4th, December 3rd. Do you want to vote?
Yeah.
Let's vote. All right. So raise your hand if you would like it on the 3rd. That's on Monday. Coming back. 1, 2, 3, 4. Whoa, more hands are coming up.
What's the other option?
Tuesday.
Okay, why would we do
Okay, hold on. Shh. Hands up high. 1, 2, 3, 4, 5, 6, 7, 8. All right, and Tuesday? That is more than 8. So here's the deal. Because I get that for some people, if we do it on the Tuesday, that means that your Tuesday is going to be nuts. If your Tuesday is going to be nuts and you would like to take it on Monday, if you want to come up with another solution, come talk to me. Does that sound fair? So we will plan to test in class on Tuesday. If that makes your Tuesday a terrible existence, let's find another time for you to do it. Deal? Cool. On that day, you're going to have your regular homework done as well as the problems that I gave you, the purple sheet that I gave you yesterday. We're going to work on some of that today, though, so, we'll kind of see where we're at. Good? Henry, do you need something, honey? Are you okay? Great. All right. So my first order of business, my first thing that I want to make sure we do is to go over any homework questions from that chapter 9, questions 8, 9, 26, blah, blah, blah. Yeah. Problems 23 and 26. Let's do it. Or 27. Thank you. All right. So all of this content, all of this stuff in this set of questions, it says homework, is dependent on the concept of, so let's make sure we understand the concept first, of conservation of momentum. So we kind of defined it yesterday, but I just want to make sure that it makes sense. What does it mean to conserve something?
To save.
To save it, to keep it the same, right? Okay? So, conserving momentum, what does that mean?
To save momentum.
To save the momentum, to keep it the same. That means that before and after, I don't know, a collision, for example, the total momentum of a system is going to be the same. I'm going to write a couple things down. You might want to write this down like in notes or something like that as well, okay? I told you a story about my student teaching experience, right? Yeah, and I told you about the question that Mr. Daniels asked all of his brilliant students, and he said, give me an example of a time when momentum isn't conserved, right? And the answer was a really easy question to grade because the answer is that it's always conserved, right? But there are a couple of caveats there that are important to note, and that is that we have to have a closed system. Closed system means no outside forces acting. Okay. What that means is that if you look at the momentum of a frog, for example, as it's falling, what's its momentum right now? 0. Remember, momentum is mass times
Time.
it's okay. Let's back up for a second. Make sure write that down. Momentum itself is defined as mass times velocity. Okay, that is the momentum of an object in any given moment. Okay, the momentum of an object can change if there's a force that's acting. But what I'm saying here is that in a closed system, there's no outside forces acting. So I'm saying multiple things at once here. Let me go back to the frog for a second. What's the momentum of the frog? 0. He's got mass, but he's got no velocity. If I watch him right now, does he have momentum?
Yes.
Yeah. So he obviously has changed momentum, right? This says that momentum shouldn't change. What's the problem with that situation, though? Is there a force acting on him?
Yeah. There's gravity, and so the velocity is just going to keep increasing, so the momentum is going to keep changing.
Right. So the game is, really, okay. Yeah. So when we have the frog that's falling, here he is, and he's got a force down, right? A force of gravity, the force of the earth acting on him, acting over a time, it's going to change his momentum. Hey, we did that already, though. That's F delta T is equal to M delta V. Hey, we did that. That's the impulse momentum theorem, right? This is magic, you guys. Are you ready for this? Some magical physics happening. Speaking of magic, put your pencil down and pay attention, hey? I know, I totally see it. It's great. But what I want is right now is for you to not be distracting your classmates. I really would appreciate that. If I have this and my force is 0, what does that tell you about the change in momentum? Oh, how cute is that? In a closed system, there's no outside force. And if there's no outside force, then there's no change in momentum. That's lovely. So really, this whole idea of conservation of momentum is just a subset of the impulse momentum theorem. No force, no change in momentum. No change in momentum, it's a closed system. Woo! All right. So in a closed system, no outside forces acting, no change in momentum. The game is, though, that a system can be more than one object. Usually when we talk about this, we talk about just the frog falling, right? There he goes. But if you have a car moving in one direction and a car moving in another direction, they interact, they collide. Do they apply forces? Yeah, but they're all internal forces. They're forces between them the things, but if you look at just that system together, that system can be multiple things. Can be multiple objects. But as long as there are no outside forces acting on the system, things pushing or pulling from the outside, then the momentum has to be constant. Okay. Ian's saying that's not the question I asked. I wanted to know about 26. Was it 26? No, 23. But this is going to help us. The equation that is not on your equation sheet. I used to teach physics, like regular physics to little ninth graders. They weren't really little. They're all bigger than me, but young ninth graders. And they would get really, really mad because the formula for conservation of momentum was not on their equation sheet. And they would cry, not literally, but they would whine about it a lot. Okay, but here it is right here. The momentum initial has to equal the momentum final. They get really mad because that wasn't on their equation sheet. Like, come on, you guys. Come on. Really? You can do that. Okay. That's real. That is the statement of conservation of momentum. The beginning and the end have to be the same. All right. I don't want Ian to get mad, so we're going to go ahead and start with number 23. I don't really think you'd get mad. Okay. So this is on the homework. A 10,000 kilogram railroad car is rolling at 2 meters per second when a 4,000 kilogram load of gravel is suddenly dropped in. What is the car's speed just after the gravel is loaded?
So we can just solve for it.
Yeah, we're just going to solve for it. So I'm going to go ahead and write down our givens and kind of make sure we understand the question, okay? But yes, I mean, literally, you're just going to like plug stuff into the equation that you're going to figure out. So you've got a car, a railroad car, like an open box car that's moving, right? And then all of a sudden, this load of gravel is going to fall into the car. It's going to land. How, if at all, do you think that load of gravel falling into the boxcar is going to affect the boxcar's speed?
Slow it down.
Slow it down? Seems reasonable, right? Yeah. Now it's got way more mass. Probably going to slow it down. All right. So let's just kind of write this stuff down. So we know that the mass of the car was, where are we at here? 10,000 kilograms. The velocity of the car at the beginning is 2 meters per second. The mass of the gravel is 4,000 kilograms. It's a lot of gravel. The initial velocity of the gravel in the horizontal direction, if it's dropped straight down, what's the initial velocity of the gravel? 0. It's not moving this way or this way, right? So we're going to say the initial velocity is 0 meters per second. See if we got our vocabulary. Is this an elastic collision or an inelastic collision? And by that I mean, how do the final velocities compare?
Inelastic.
The velocities will be the same, right? Because the gravel's going to stay in the car. So that means that the velocity at the beginning, the velocity at the end for the train and for the gravel will be the same. So I'm going to go ahead and write that down, that the final velocity for the car equals the final velocity for the gravel. And I think that that's really what we wanted to know. So we're going to start with the equation that my ninth graders were so mad that wasn't on their equation sheet. The momentum at the beginning equals the momentum at the end. I'm going to write this out in a lot of steps because it's the first one we've really done together. You do not have to write all these steps out. You guys know that. I just want to make sure that it's clear. Okay? Momentum of anything is equal to the what times the what of that object? The mass times the velocity. So we got the mass times the velocity of the cart at the beginning plus the mass times the velocity of the gravel at the beginning. So that's the total momentum at the beginning has to equal the total momentum at the end. I will tell you, even though I'm saying you don't need to write it out a bunch of times, when you're doing a problem like this, especially, I don't know, like on a test or something, or on your homework that you're turning in to show me that you've done something, I do want to see some of this. Like, I need to see a statement of conservation of momentum. If I don't see a statement of conservation of momentum, I don't know that you know it. It might just be convenient, or you may have just, grabbed it off of somebody else's paper. Okay? MGVFG. So this right here is the statement of conservation of momentum. Okay. And now, this is just algebra, right? We can get rid of stuff. Is there anything here that we can just get rid of? What'd you say, Rihanna? We can put them together. Yeah, we can put them together. So we can say that this is equal to, you can just, we say like MC plus mg times the final velocity, like that. Is that kind of what you're thinking? Yeah, absolutely. Yeah. Anything else that we can do to make our life a little bit easier?
mg vig.
This one goes away because the initial velocity is 0. Yeah. So we've got the mass of the car times the initial velocity of the car is equal to the sum of the masses times the velocity. And now it's pretty straightforward, right? Plug in some numbers. Okay. Does that setup make a little more sense? It's kind of mean that I threw this all at you without, having gone over any of them. I apologize about that. I'm going to scroll up. Was it 26 or 27? 27 was the other one. Okay.
Wait, why did you combine the final velocities into one?
Here?
Yeah.
Because they both have the same final velocity. And it just makes it easier because I have one thing I don't know. Does that make sense? Because these two final velocities are the same.
I know this again. I don't understand.
Because when the gravel falls into the cart, then it's all going to move together. Is that okay?
Because it's inelastic. They have the same one.
Correct. Yes. Yeah. Bless you. So 20,000 divided by 14,000, which is something.
Yeah, it's 1.7.
It's going to be something a little smaller than 2, right?
Yeah.
20, 1.43. That should make pretty good sense. Your gut feeling was that it was going to be slower, right?
Yeah.
I would double check and make sure that makes sense to you. Sure. And the mass here is not, it's not the same as the mass here. So it's going to slow down, but it's not going to slow down by like half or something. Bless you. Okay. Yeah.
So you said you need a statement of conservation of momentum
Yes.
for the test.
Yes. Yes. Yeah. Because otherwise, what often happens with people for whom mathematics is very straightforward is that they get this and then their head just goes boom and then they get an answer. And as much as I believe in you all and I know that you're brilliant and I've been working with brilliant kids for a long time, I totally get that. I need to see this physics principle. That's the thing I need to see to show me that you really understand it. It wasn't just convenient. Because sometimes in conservation momentum problems, there are some situations where 2 wrongs, like you screw 2 things up and it actually fixes the problem. Do you know what I'm saying? I don't know if that's ever happened to you in other math problems or science stuff, but I want to actually see this so that I know that you're doing it right.
So it's kind of like an equation, but in a different sense.
Exactly. Yeah. Show me the physics is really what I want.
So if we don't have that, we'll lose points on every quiz.
Indeed.
Our homework too.
Indeed.
All the points.
Yeah.
All the points.
Everything.
See, you got everything else right.
Oh, okay. I thought you were going to
Write it down.
get mad at you. Okay. All right. Let's take a look at this bird flying along. Is that the one we're doing?
Yeah.
Yeah. Okay. So this one is very similar. Let's take a look. 27?
Oh, wait, we even question the problem.
Problem. 300 gram bird. So here's my bird. Flying along at 6 meters per second. Sees a 10 kilogram insect heading straight toward it. Oh, that's interesting.
It's fine.
A 10-gram insect flying this way. Okay. The bird opens its mouth and the bug just goes in. I feel like it's like some really silly cartoon. That's what I'm imagining here, right? So there is a collision, an inelastic collision. Would you agree? No, and then they keep going, right? Same story. So it's the same kind of problem. The only thing that's really different in this one, I'm not going to go through the whole thing probably, but in this one, now the initial velocity here is not 0. So you've got this thing. One thing that's really important, the bird is going this way, the bug is going this way. What does that mean about one of their velocities?
It's negative.
It has to be negative. Bird is going this way, bug is going this way. So make one of them negative. I don't care which one, it does not matter. But you need to make one of the initial velocities negative. Okay? Do you want me to go through that or is that okay? Does that make sense what we need to do?
Can you like write down all the givens?
For sure. Absolutely. Yeah. So the mass of the bird was 300 grams. So in this case, do you have to convert it to kilograms? Nope. Because it's all going to go away. All the masses are going to go away. So the mass of the bird is 300 grams. The initial velocity of the bird is 6 meters per second. The bug, that's silly. They're both bees. The mass of the bug is 10 grams. And the initial velocity of the bug then is negative 30 meters per second, right? That negative is the key to the problem. If you don't have that negative, then it will be wrong. Like everything's not going to work. Do you know what I'm saying? Okay. We know that the velocity final of the bird and the velocity final of the bug are going to be equal, and that's what we're looking for. That's what we're trying to find. Okay. So you can say MB, V initial B, plus M U, V initial U, is equal to, now you can either write it as a separate thing, or if you want to put them together, you totally can. You can say the mass of the bird plus the mass of the bug times the final velocity, because it's an inelastic collision. And again, you're solving for VF. The mathematics here is not hard in general. Okay? The actual calculation is not the biggest challenge. The biggest challenge is figuring out your givens and then making sure you plug stuff in right. Questions, issues, concerns, things that you would like to discuss? Are there any others of the homework questions that you would like to go over? That wasn't technically interesting. You seemed like you were in need of a calculator. Okay. Hearing no other questions on the homework, I think that the only other thing I had on my list of things to do was to do some more practice. And then, again, the last 5 minutes, I want to do the survey stuff. So I am happy to go through things with you. I am happy to just let you guys work and answer questions. Do you have a preference? What would you like to do?
Work and answer questions.
Work and answer questions is one vote?
Yeah.
Yeah, I'll do one with you?
Okay.
Yeah? Okay, I'll do the first one with you. So this Gonzo problem is kind of, well, it's a little bit like the opposite of the train problem. Hold on just a second. I'm going to try and be a little clever here. Make it bigger. There we go. All right. So here we go. Gonzo is going to jump off of a canoe that's initially at rest. So let's draw a picture. Pictures are not required for these problems, friends, but sometimes it's just easier to kind of imagine what's going on if you draw a picture. So I'm going to go ahead and draw my picture. Here's my canoe. There's the water. Here's Gonzo with his little orange life jacket on. Okay, there we go. So at the beginning, well, we can write down our givens. The mass of Gonzo is 55 kilograms. The initial velocity of Gonzo is what? You guys all have this problem, right? Do anybody need it? You all have it? Do you need one?
What?
I'm not. That was not very kind. All right. So here he is. He's standing on the edge of the boat. Like, I'm going to go. It's going to be so exciting. Yay! What's his velocity, guys?
0.
We're assuming it's a still lake.
It's still
0.
Zero. He's not going anywhere.
Zero.
Yeah. Not frictionless water. It doesn't even watch. Tell me about the boat. The mass of the boat is 250 kilograms. The initial velocity of the boat is
0.
how much?
0.
0 is not going anywhere yet.
Oh.
Not going anywhere yet. He's going to jump off in this direction. So they have a total momentum of how much at the beginning? Without even doing the math, we can figure it out. 0, right? Because there's no velocity, so no momentum. So that means that the total momentum at the end has to be how much? 0. So he's going to jump off and go this way, splash into the water. Where is the canoe going to go, friends? That way.
Wait.
The momentum of Gonzo is going to go this way. The momentum of the canoe has to go this way because they have to add up two. Question.
Jump at us. He's jumping off the front to the right. Right?
I don't care.
No, I'm
I
not.
don't know what you're asking.
So he's jumping off the front of the canoe.
Oh, I see what you're talking about.
Oh, so he's facing the front.
He's facing the front of the canoe. That says he jumps to his right.
Well, who cares? I mean,
No,
whatever.
he jumps off the front.
To the right, though.
Don't worry about it. Don't worry about it.
Okay.
I don't care. You're standing back here.
Okay.
Yeah, is that better?
I don't-
Or something? I mean,
I was genuinely So he's
jumping that way. What's your problem?
he's facing the front.
No, he's not. If that's the front.
No, it doesn't. It's bad.
You're wrong, though. I don't want you to tell me that I'm wrong.
No, I don't think you're wrong.
Okay.
I just think it's confusing.
Oh, okay. All right, let's move on and do physics, eh? Here we go. Regardless, the reason that this is important, because I don't want to ignore it. The reason that this is important is that when you answer this question, this part does matter. When you answer the question of what the velocity of the canoe is, you do need to specify that the direction of the velocity is opposite the direction of Gonzo's velocity. Are you with me there? So those directions do matter. Yeah. So we know, so we're looking for, it says the final velocity of Gonzo is 7.5 meters per second. And we want to know the final velocity of the boat. Okay. So the statement of conservation of momentum here, the initial momentum has to equal the final momentum. Again, the reason that I don't just spew the conservation of momentum equation at you or give it to you on a equation sheet is that in this case, this one is just going to be 0. And if you just want to start there and say, hey, that's got to be 0, okie dokie, that's fine. So 0 is equal to the mass of Gonzo times the final velocity of Gonzo plus the mass of the boat times the final velocity of the boat. So you got 55 times 7.5 equals 250 times something. But if you just write this down and then you give me an answer, I'm good with that, friends. That's totally fine with me. I can't do the calculations because Grace totally can't. I'm just teasing. I could totally go walk and get another one. How are we doing? Are we okay? Yeah.
Also use the change momentum of 150 equals negative change momentum.
For sure. It's the same thing. Yes, absolutely. Did you guys catch Jasmine's question? Does that make sense?
No.
Ask it one more time loudly so everybody can hear you.
Like I saw this one equals change
So basically what we did in the lab. Change of momentum of Gonzo equals the change of momentum of the boat. Which is, it's just a rearrangement of the statement. Either one is fine. Mm-hmm. Yeah. Do you want to look at one more or are you guys good? You want to just want to work? Okay. I'm going to let you work for about 7-8 minutes. Go get started.
To the left, to the left, to the left.